So today I wanted to talk about the topic of complex numbers. Typically complex numbers are represented as three different forms. So first you have the Cartesian coordinates. So this is also known as rectangular form. And it takes something like this, where z equals a plus bi, where a is a real number and b is imaginary. And second are polar coordinates. This is where you have r, which is the magnitude, times cos theta plus I sine theta. And lastly, we have exponential form. Some people may call this Euler's form. And that's because the incorporation of e as a constant. Again, it has the real number r, or the magnitude, sorry. So let's take a look at some examples of this. So there's always going to be some form of conversion from one type of coordinates to another. So let's take the first example. Let's say we're given a Cartesian coordinate, z equals 2 minus 2 root 3i, and we're going to convert this to polar and exponential form. So first, let's write out the equation for the polar coordinates. So where do we get theta and where do we get r? R is simply the magnitude. So we take this, we get 4, giving us root 16 equals 4, so r equals 4. So how do we solve for theta? There's two different ways to solve for theta when trying to get to polar coordinates. My favorite method is using inverse tan of b over a, and then simply using your triangle identities to find out the answer. So let's write that out. So here we can see the 2 cancels. And using our identity, this is minus pi over 3. And simply, we can now plug it in. So r was 4. Cos of minus pi over 3 plus I sine theta again. And that's our polar coordinates, our Cartesian to polar coordinates. And now how do we get this to exponential form? So again, we've just done step 1. We'll just get it to polar coordinates. So now we just take a look. R and theta. And remember, the form of exponentials follows this. So we simply just look at it and plug it in. And that's the equation for the exponential form. Another way to find the polar coordinates is also through 2 formulas. You can also do instead of inverse tan, you can do cos theta equals a over r, and sine theta equals b over r, which pretty much follows the same thing because you will have to do sine over cos to get tan. So say we're given a polar form or a polar equation of this, and we want to get the Cartesian and exponential equations. To get it into Cartesian, we simply just evaluate it. So 5 times, what is cos 5 pi over 4? So if we do our special triangles, we also know in quadrant 3, and both cos and sine are negative in quadrant 3. And so what's the reference angle? Pi over 4, right? This is a form I like to know I like to remember for the special triangles. Basically, these are the pi's, this entire first column, and then this is the cos and sine. So pi over 4, that's root 2 over 2. And because in quadrant 3, it's negative. And again, that's also the same here. So it's root 2 over 2. So our answer for the Cartesian coordinates. Oh, sorry, I forgot to bring down the I over here. It's 5. That's our answer for the Cartesian coordinates. Now, how do we get this from polar to exponential? Again, we just take a look at our form for exponential. Our r is 5. E is a constant. Our theta is 5 pi over 4. I. And that's our exponential. Now, how do we get from exponential from polar or Cartesian? There's simply the same steps. So again, we can just look at this and expand it. So we know that our polar coordinate form is in the form of r cos theta plus I sine theta, like that. Our r is going to be 3. Our theta is pi over 6. That's simply it. And then again, we can infer what our Cartesian coordinates are from this, based off our special triangles again. So we got 3 times cos pi over 6, which we know 3, 4, 6, root 3 over 2. And then sine pi over 6, which is 1 over 2. So we'll get something like this. That's our Cartesian coordinates. And that's how you solve Cartesian coordinates, polar coordinates, and exponential form